Hi everyone, welcome to goclasses. In this lecture, we will study regular grammars. Also, we will study right linear grammars. Okay, so let's do the recap. So far, what we have seen. So far, we have seen context-free grammars, which are also called CFG. So, in the context-free grammar, what the definition of context-free grammar? We have seen context-free grammar is four tuple, or I can say there are four components in the context-free grammar. We have variables, or I can say non-terminals. There is alphabet, or I can say terminals. There are production rules, or I can say substitution rules, and there is start variable from where we will start our derivation. Okay, so very simple point. So you can easily see what is V. This is a finite set of variables or non-terminals. What is sigma? This is finite set of terminals, or I can say alphabet. Okay, so you can see sigma comma V, they are disjoint because here V means variables. Okay, this means non-terminals, and sigma means terminals, or I can say sigma means alphabet. For example, you can see this is alphabet, so this can be your sigma. Okay, and there is S, which is the start variable. So start variable, this is a variable, S belongs to V. Okay, so our derivation will always start from the start variable. And what is this production rules? Production rules, remember, in the context free grammar, every production rule has this format where LHS has single variable and RHS can be any sequence of terminal comma non-terminal. Okay, so very simple point. Remember, in this context free grammar, you can notice we have some rules, yes or no, production rules we have. So remember, in the production rules, in every production rules, the every in every production rule, the LHS will be a single variable. The LHS will be a single variable. And remember, RHS can be anything. For example, RHS can be any sequence of variables comma terminals. Okay, it can be any sequence of variables comma terminals. Okay, so for example, this is also fine. Okay, any sequence of variables comma terminals is fine. This is also fine. Very simple point. So remember, in this context free grammar, every production rule is like this. Every rule has this format that on LHS we have single variable, and on RHS we can put any sequence of variables or terminals. Okay, so we can put epsilon also, because you can see from here we can generate epsilon also. We can generate any sequence of variable comma terminals. So this is the definition of context free grammars that we have seen in the previous lecture. Okay, now we have seen the language of context free grammar, that is called context free language. For every context free language there is context free grammar. So very simple point, if you have a context free grammar G, if you have a context free grammar G, then remember the language will be called, the language of G, that will be called CFL, context free language. And for every context free language there is a context free grammar. So very simple point. Now let's see. So we have seen what is a context free language. A language of context free grammar, I can say a language is context free if there is a context free grammar for this language. Okay, and what is the language of a grammar? For any grammar G, the language is set of all strings that can be generated. Set of every string, set of all string that we can generate from the start variable. Now we will study what are regular grammars, also what are right linear grammars. So let's see the definition. Let's see the definition of right linear grammar first. What are right linear grammar? These are a special type of context free grammars. Remember, every right linear grammar, this is a context free grammar, but these are a special type of context free grammars. The name itself is telling you these are right linear. Okay, see what is the definition. In the right linear grammar, again we have total four components. We have variables, means non-terminals. We have alphabet, means terminals. There is a start variable, and there are production rules. Okay, now which type of production rules we allow in the right linear grammar? That is the definition of right linear grammar. So let's see what type of production rules we allow. Okay, so let's see the production rules. So production rules P, let me tell you, every production rule will be like this. Either a single variable going to a sequence of terminals, okay, or a single variable going to a sequence of terminals followed by a single variable. Okay, followed by a single variable. So this is the simple idea, very simple, that remember, in the right linear grammar, the name itself is telling you this is right linear. Okay, so it means that on the RHS, in any production rule, on the RHS, either we have no variable, you can see the sequence of terminals, either we have no variable. Okay, what is this T? This T is basically sigma. I told you this T is the same as sigma. Okay, and these are called alphabet, or you can call them terminals. Okay, for example, you can have A comma B. Okay, so very simple point. Remember here that every production rule will be like this, that you have a single variable on LHS, and on the RHS you can have no variable. For example, you can see, okay, here you can see this is a sequence of alphabet symbols. Or what you can do, or you can do sequence of terminals followed by a single variable. So this single variable will be at the rightmost position. Okay, you can see this will be at the rightmost position. So this is the idea. So let's see the definition. Right linear grammar, these are special type of context free grammars where each production rule has at most one variable. Each production rule has at most one variable, and remember, this variable will be on the rightmost position. So very simple point, remember, the production rule will be like this, that you can have a single variable going to a sequence of terminals, or a single variable going to a sequence of terminals followed by a single variable. Okay, so on the RHS of any production rule, you can have at most one variable, and that variable must be on the rightmost position. You can see that variable must be on the rightmost position. So this type of production rules are allowed in the right linear grammar. Okay, no other production rule is allowed. Very simple. Let's see this example. Tell me this grammar. Look at this grammar and you look at every production rule. Is it right linear grammar? The answer is yes, because here you can notice we have total 5 production rules. Yes or no? In this grammar, if you notice, there are total 5 production rules. So let me write it here. The 5 rules are like this. 5 rules are: S I can replace with AA, S I can replace with B, A I can replace with AAB, and you can notice that B I can replace with BB, or B I can replace with A. Okay, so you can easily see in this grammar, you can see that on the LHS we have single variable, that is fine. So this is a context free grammar because on the LHS of every rule we have single variable. But you can see this is a right linear grammar also, because on the RHS of every rule we have at most one variable, and that variable is on the rightmost position. You can see there is at most one variable, and that variable is on the rightmost position. At most one variable, that variable on the rightmost position. Here also at most one variable, there is no variable, that is fine. Okay, you can see at most one variable, and that variable is on the rightmost position. So you can see this is a right linear grammar. Okay, now let's move on. Let's see this grammar. Tell me, is this right linear or not? This grammar. So you can see this production is fine. Yes or no? This production, because here we have a single variable on the right side, and that is fine, and that variable is on the rightmost position. This is also fine. This is also fine, but this is not fine. Yes or no? This is the violation. This is the violation of right linear grammar. Okay, this means right linear grammar. Right linear grammar. Okay, is this clear? So remember this grammar, this is not a right linear grammar. This is not a RLG. Okay, is this clear? Because you can see here we have a single variable, that is fine, but that single variable is not on the rightmost position. Right linear grammar means on the RHS of every rule we must have a single variable, at most one variable we must have, and that variable must be on the rightmost position. Okay, but this is the violation. Now let's see what is a left linear grammar. The definition is again very simple. Left linear grammar, these are a special type of context free grammar. So in the left linear grammar, what we have? In the left linear grammar, we have total 4 components. We have variables, we have terminals, we have start variable, and there are production rules. Okay, now let's see what are the production rules that are allowed. So the production rules that we allow in the left linear grammar, these are like this, that a variable can go to a sequence of terminals, means there is no variable on the RHS, or a variable can go to a, a variable can go to another variable followed by a sequence of terminals. Okay, is this clear? So you can see here on the RHS of every rule, in every rule on the RHS we have at most one variable, and that variable must be on the leftmost position. So this is the definition of left linear grammar. Okay, on the RHS of every rule we must have at most one variable, and that variable must be on the leftmost position. Simple. So you can see left linear grammar are a special type of context free grammar where each production rule has at most one variable on the RHS, and that variable must be on the leftmost position. Okay, so it is like this. A variable can go to a sequence of terminals. So you can see on the RHS there is no variable, that is fine. Or a variable can go to another variable followed by a sequence of terminals. So you can see in every rule on the RHS we have at most one variable, and that variable must be on the leftmost position. This is the definition of left linear grammar. For example, this grammar, is this left linear? Here, look at every production rule. This production rule is fine because in this production rule, in this rule, we have at most one variable, and that variable is on the leftmost position. So this is perfectly fine, correct? Okay, this is also fine. This is also fine because here you have at most one variable. So there is no variable, that is fine. Okay, so this is also fine. This production rule is also fine. This is also fine. This is also fine. This is fine. Here you can notice we have at most one variable, and that is on the leftmost position. So this is also correct. And this is also fine because here you have no variable. Okay. So very simple that this grammar is a left linear grammar. Is this clear? So this grammar is a left linear grammar. Okay, so very simple definition: left linear grammar, right linear grammar. What about this grammar? In this grammar, you can notice this production rule is fine. Yes or no? This rule is perfectly fine because here you have on the RHS you have at most one variable. There is one variable, and that is on the leftmost position. This is also fine, but you can notice this one is also fine. That is also fine. Okay, but you can easily notice that this is not fine. Yes or no? So here you can see this is the violation. This is the violation of left linear grammar. Okay, is this clear? So remember this grammar G, this is not left linear grammar. Okay, this grammar is not left linear grammar. Now, now let's see the definition of regular grammar. What is regular grammar? Because regular grammar will generate regular language. So what is a regular grammar? Every right linear grammar is a regular grammar. Also, every left linear grammar is a regular grammar. So very simple definition. What is a regular grammar? Every right linear grammar is regular. Also, every left linear grammar is regular. Okay, so remember, every production rule either must be right linear, or every production rule must be left linear. You cannot mix. You cannot mix right linear and left linear. Okay, is this clear? Simple point. Remember, regular grammar means either it must be completely right linear, or it must be completely left linear. Okay, understood? Either it should be fully right linear grammar, or it should be fully left linear grammar. So what about this grammar? Tell me. Here you can easily see in this grammar, because of this rule, this is not left linear. Yes or no? Because of this rule, I can say G is not left linear grammar. And you can see because of this rule, I can say G is not right linear grammar. Okay. So finally, I can say this is neither, this is not left linear grammar, this is not right linear grammar. So what I can say, this is not a regular grammar. Is this clear? This grammar, this is not a regular grammar. Okay, understood? So what is a regular grammar? It is a right linear grammar, or it is a left linear grammar. But you should not mix right linear and left linear. It should be fully right linear, or it should be fully left linear. That is the definition of regular grammar. And regular grammars will generate regular language. Means every right linear grammar is regular grammar. So this will also generate regular language. Every right linear grammar that will generate regular language. Every left linear grammar that is also regular grammar. So that will also generate regular language. So you can see every RLG generates regular language. Every LLG generates regular language. Okay. Tell me the answer for this question. Which of the following grammars is right linear? Let's see. So you can easily see this grammar is not right linear because here you can notice on the RHS we have a single variable, but that is not on the rightmost position. Yes or no? So you can see this is a context free grammar. because on the LHS of every rule we have a single variable. Okay, so this is a context free grammar, but remember this is not a right linear grammar. You can see because of this rule this is not a left linear grammar. So I can say this is not a regular grammar. So I can say this is not a regular grammar. Okay, what about the next one? This one, here you can notice this production is fine, this production is fine, this production is fine, this production is fine. So this is right linear grammar. The question is asking, is this right linear? So yes, this is right linear. You can see this is context free grammar also. Okay, because you can see on the LHS you have a single variable, on the RHS you can have anything. So this is a context free grammar also. You can see this is not left linear. This grammar is not left linear. Why? What is the reason? Because of this production rule. Because of this rule, this grammar is not left linear. Okay, and what about this one? Here you can notice in this rule on the RHS we have more than one variable. So this is not a left linear grammar. This is not a right linear grammar. Okay, this is not a left linear, but this is context free grammar. Okay, is this clear? Because you can see on the LHS we have a single variable. In the context free grammar on the RHS you can have anything. So this is a context free grammar, but this is not left linear grammar, this is not right linear grammar. So the answer will be this one. This is not the answer. Okay, and because this is neither left linear nor right linear, so I can say this is not regular grammar. Okay, so very simple. Tell me the answer for this question. Which of the following statement is true about the grammar that is given to you? The question is asking you which this grammar is this left linear or is this right linear. So let's see this. Here you can notice in this production, because of this production, this grammar cannot be left linear. Yes or no? This grammar is not left linear because of this production. Okay, you can see right linear production, right linear production. This is also fine. This is also fine. So I can say this grammar is actually right linear. Okay, this grammar is right linear. Every right linear grammar is a regular grammar. So this is regular grammar also. This is not left linear. So what will be the answer here? You can see the grammar is right linear, but this is not left linear. Answer will be option C. What will be the answer for this question? The following grammar is S I can replace with A or B, A I can replace with A, B I can replace with B or B. So tell me this grammar. You can easily see these productions are fine in both LLG, both RLG. Okay, yes or no? So you can easily see this is left linear also, this is right linear also. Okay, this grammar is a left linear grammar also. This grammar is a right linear grammar also. Okay, so finally your answer will be that this is both. None of the other answers is correct. Okay, yes, this is the correct, because remember this grammar is actually both left linear and both right linear. Okay, because here you can see in this grammar, okay, this rule, this is allowed in both LLG comma RLG. This is allowed in both LLG comma RLG. This is allowed in both LLG comma RLG. This is allowed in both LLG comma RLG, and this is allowed in both of them. Okay, so remember this grammar is basically regular grammar. This is LLG also, this is RLG also. Okay, is this clear? A student is asking, what about S generating epsilon dot V? First of all, epsilon dot V, that is basically same as V. Okay, that is basically same as V. Yes or no? So this is actually V only. So finally you can see this is allowed in both RLG. Okay, this is also allowed in LLG. Okay, is this clear? Now, tell me the answer for this question. So this grammar is given to us and the question is asking what is this grammar G? The question is interested in the grammar G, not in the language. The question is asking this grammar has which property. So you can easily see that this production is allowed in LLG. Okay, so because of this rule, I can say that this is not RLG, this is not right linear grammar. Yes or no? Okay, but this rule is allowed in LLG, left linear grammar. Here you can notice on the RHS you have single variable, that variable is on the leftmost position. This rule is allowed in the left linear grammar. This is also allowed, this is also allowed. So finally your answer will be this is a left linear grammar. Okay, and remember every left linear grammar that is a regular grammar also. This is a left linear grammar. So every left linear grammar that is regular grammar also. So this is regular grammar also. Okay. So you can see the remaining options are wrong. The answer will be option B. Okay. A student is asking, what about this? A going to B S, B going to epsilon. So here you can notice that in this rule, look at the first rule. In this rule, on the RHS, we have more than one variable. Yes or no? So this is neither left linear. This grammar is not left linear. This grammar is not right linear. So this grammar is not regular grammar. This grammar is not regular grammar. Okay, is this point clear? So very simple. This grammar, this is neither left linear nor right linear, because you can easily see that in this production rule on the RHS you have more than one variable that is not allowed in left linear comma right linear. Okay, very simple. A student is asking S deriving B. Okay, so this rule is allowed. This rule is allowed in both LLG also. This is allowed in LLG also. This is allowed in RLG also. In both the grammars, this rule is allowed. Okay, is this clear? Because here you can notice on the RHS you have a single variable, and that variable you have a single variable. That variable is leftmost position also. This is rightmost position also. Okay, is this clear? So yes, this is allowed in the regular grammar. This is allowed in LLG, RLG. So this is allowed in regular grammar. Okay, so just apply the definition. Just apply the definition of LLG. Just apply the definition of RLG. Remember what LLG says. Left linear grammar says that every rule must be like this. A variable is either going to sequence of terminals, or a variable is going to another variable then sequence of terminals. This is LLG. Okay, so remember on the RHS we must have at most one variable, and that variable must be on the leftmost position. Just apply the definition. The right linear grammar says that a variable can go to a sequence of terminals, or a variable can go to sequence of terminals followed by another variable. So on the RHS of every rule, we must have single variable, at most one variable, and that variable must be on the rightmost position. Just apply the definition of LLG, RLG. If your grammar is LLG, then your grammar is regular grammar. If your grammar is RLG, then your grammar is regular grammar. But you cannot mix. You cannot mix RLG comma LLG. For example, you cannot do this, that okay, that you are doing LLG also, RLG also. This grammar, look at this grammar. This is not a LLG. Okay, this is not a right linear grammar. This is not a left linear grammar, because this is neither right linear nor left linear. So this is not regular grammar. This grammar is not regular grammar. Okay, is this point clear? Very simple point. Tell me the answer for this question. This grammar is given to us. This grammar can be classified as. So how can we classify this grammar? We can easily see that because of this rule, the grammar is not right linear grammar. Okay, yes or no? And because of these rules, I can say the grammar is not left linear grammar. Yes or no? So remember, this is not left linear. This is not right linear. So, so automatically this is not regular. Automatically this is not regular grammar. Okay. So your answer will be what? That will be context free grammar. Because remember, in the context free grammar, what we need? In the context free grammar, we have a single variable going to any sequence of variables, comma, terminals. So this grammar is context free. Tell me the answer for this question. This grammar is given to us. What type of grammar is this? So here we can see, first of all, yes, this is context free grammar. Yes or no? In the context free grammar, we have a single variable can go to any sequence of variable comma terminals. Okay, so yes, this is a context free grammar because on the LHS you have single variable. In every rule on the LHS you have single variable. So yes, this is context free grammar. What about the remaining? You can see this is right linear. This production is allowed in right linear. This is also allowed in RLG. This is allowed in RLG. So yeah, yes, you can easily see this is a right linear grammar. Every RLG is a regular grammar. Every RLG that is a regular grammar. So I can say your answer will be right linear. Also your answer will be regular grammar. So your answer will be basically not left linear grammar. Yes or no? Because this production, look at this production. This production is not allowed in LLG. Because of this production, I can say that this grammar is not left linear grammar. Okay. Tell me the answer for this one. This grammar is given to us. There are two production rules in this grammar. Okay. So what will be the answer? Here you can notice this rule on the RHS. We have a single variable, but that single variable is not on the leftmost position. That is not on the rightmost position. So actually, because of this rule, I can say this grammar is neither left linear nor right linear. Yes or no? The grammar is not right linear. The grammar is not left linear grammar. So automatically I can say the grammar is not regular grammar. Okay. But yes, this is a context free grammar. Okay. So the answer will be, remember, neither it is left linear nor right linear, not regular. This statement is correct. Okay. Yes or no? This option is correct. This grammar is not. Yes, this is a grammar. So the answer will be option C. Okay. This will be the answer. Now let's move on. So we have seen the definition of right linear grammar and we have seen the definition of left linear grammar. In the right linear grammar, you can see every production rule will be like this. Okay, here you can notice a variable, a single variable is going to a sequence of terminals. X is a sequence of terminals, or a single variable is going to a sequence of terminals followed by a single variable. Okay. Similarly, in the left linear grammar, we allow this type of production rules. What is the regular grammar? This is basically either left linear or right linear, but you cannot mix. Tell me the answer for this question. Every regular grammar is context free grammar. Yes, this statement is true because in every regular grammar on the LHS we must have a single variable. In regular grammar on the LHS we must have a single variable. Single variable is going to something something. So that is the reason I can say that every regular grammar is a context free grammar. Okay. Next, let's see this. Every regular grammar will always generate regular language. If your grammar is regular grammar, then it will always generate regular language. Okay, and you know that every right linear grammar is regular grammar. So every RLG will also generate regular grammar, regular language. Every LLG, every left linear grammar is also regular grammar. So every LLG will also generate regular language. So very simple point. Every regular grammar will generate regular language. RLG will generate regular language. LLG will generate regular language. Very simple. Now tell me the answer for these two questions. Let me know. The first statement is a regular grammar will necessarily generate regular language. This statement is true, right? Okay, if your grammar is regular, then it will definitely generate regular language. What about this one? A non regular grammar will definitely generate non regular language. This statement is false. This statement is false. Okay, let's see example. Remember, this statement is saying that a non regular grammar will definitely generate non regular language. This statement is actually false. But this statement is true. A regular grammar is generating regular language. That is always true. Okay. So consider this example. Tell me, is this grammar regular or not? First, you tell me that. Is this grammar regular or not? You can easily see this grammar is not right linear. This is not right linear grammar. Why? What the reason? Because of this. Because of this rule, I can say the grammar is not right linear grammar. Okay. Why? What the violation? Let's see the violation. The violation is this variable is going to cc. So you can see this is the violation. And this grammar, you can see this is not left linear. Why this is not left linear grammar? Because you can easily see there is a violation. What is the violation here? The violation is s going to ax. Okay, yes or no? So you can see this is the violation of left linear. So this is neither left linear nor right linear. So I can say this grammar is not regular grammar. Yes or no? This grammar is not regular grammar. But what is the language? Now you tell me what will be the language here. Can you find the language? And you tell me the language is regular or not. Let's see this one. What will be the language here? So it is actually very simple. If you notice what this C will generate, what this C will generate. So here from C, from this variable C, we can generate C star. Yes or no? Because you can notice this C I can replace with C or epsilon. Okay, so from here, what I can generate? Notice from here I can generate epsilon, I can generate C, I can generate double C, I can generate C cube, C power 4, and so on. Okay, so very easily you can see that the C will generate C star. Okay, so now you tell me what X will generate. Let me know what X will generate. What will X generate? So X will generate either this variable, this string B. X will generate string B, or X will generate C and C will generate C star. Yes or no? So X will generate B or C star. Okay, so tell me what S will generate. Let me know what will S generate. S will generate AX. Okay, and that is what? That is A. What X will generate? X will generate B or C whole star. So remember, what S will generate, that is the language. So what is the language of the grammar? Finally, the language of the grammar will be A, B or C star. This is a regular expression. Do you agree? This is AB or AC whole star. So you can see this is a regular expression. Because this is a regular expression, so the language is regular. If you can write regular expression, then the language is regular. Yes or no? Okay. So very simple. I can say that the language is regular. Understood? So remember here, the grammar is not regular. If you focus on this grammar is not regular. This is not a regular grammar. Okay. If the question is asking you grammar is regular or not, so the grammar is not regular grammar, but the language is regular. The language it will generate, that is regular. That is regular language. Okay. Is this point clear? So remember this statement, when I say that non-regular grammar will always generate non-regular language, this statement is true or false? Tell me. Non-regular grammar will generate non-regular language. This statement is false. Okay, is this point clear? This statement is false. Non-regular grammar may or may not generate non-regular language. Non-regular grammar may generate regular language or it may generate non-regular language. It will depend on the grammar. Let me give you another example. Consider this one. S going to SS or A. Okay. So you tell me, this grammar, is this regular grammar? A simple question I'm asking, this grammar, is this regular grammar? Definitely not. This is not a regular grammar. Why? What is the reason this is not a regular grammar? Because you can see this is not a right linear grammar. This is not right linear grammar. This is not left linear grammar. And because this is neither RLG nor LLG, neither right linear nor left linear, so I can say this is not regular grammar. Okay, yes or no? But you tell me what is the language. Okay, now you tell me what is the language here. Can anyone tell me what is the language? Let me know. So here, if you notice, what will be the language? That is, from S you can generate A. Okay, what else you can generate? From S I can generate SS, and then I can generate double A. Yes or no? I can generate triple A also. I can generate, for example, this S can go to S S S. Then I can generate triple A also. I can generate 4A also, 5A also. Yes or no? So from here you can easily see that S can generate, from S I can generate basically A plus. Yes or no? And this A plus, this is a regular language. Is this clear? This language is a regular language. Okay, so remember grammar is not regular, but language is regular here. Is this point clear? Please tell me. So here also you can easily see that here G, okay, let's call it G. So this G is not regular, but the language is regular. Okay, understood? Please tell me. Okay, so now you tell me. So far, what I told you that non-regular grammar, if you have non-regular grammar, then it may generate regular language. Yes or no? It may generate regular language. It may generate regular language, but it is may or may not. Let me tell you, it is may or may not. Let me tell you, it is may or may not. Means if you have a non-regular grammar, then it may or may not generate regular language. It may generate regular language. For example, here the grammar is non-regular, but it is generating regular language. Okay, or it may not generate regular language. Let me give you this example also where non-regular grammar will generate non-regular language. Okay, so consider this grammar. Here you can notice this grammar is a non-regular grammar. Yes or no? Look at this grammar. What is this grammar? Here you can notice this is neither right linear nor left linear. So this grammar is what? Tell me. You can notice this grammar is not left linear grammar. This grammar is not right linear grammar. So what is this grammar? This grammar is not regular. Yes or no? This grammar is not regular grammar. But you tell me what are the language here? This grammar is not regular grammar. Now you tell me what is the language for this. If this is the grammar G, so what is the language here? You can easily see that we have these production rules. S, from the variable S, I can replace with AA, or I can replace with epsilon, and this A I can replace with SB. You can apply the substitution rule. Yes or no? What you can do, you can apply the substitution rule. Okay, because you can notice when you go to A, when this S will go to this A, then this A will go to SB. Okay, so what I can do, I can apply the substitution rule, and I can say that basically A, remember when I go to A, when S will go to A, then A will go to SB. So this A will replace with SB. Yes or no? This A will replace with SB. Already there is epsilon. Okay, and there is a this. Now you can easily notice in this grammar A has become unreachable. Yes or no? In this grammar, this variable A has become unreachable from the start variable. From the start variable, can you reach variable A? Let me know. Look at this grammar and tell me. From the start variable, can you reach variable A? No, you cannot reach variable A. So here now you can see that A, this has become unreachable. Because this has become unreachable, so you can remove it. Okay, so finally, your grammar will become A, S, B, or epsilon. And you know what are the language it will generate. What will be the language generated by this grammar? This is the standard grammar for A power n, B power n, where n is greater than equal to 0. Okay, so remember here, the grammar is non-regular. The grammar is non-regular, and the language is also non-regular. Yes or no? The language, that is also non-regular. Understood? Please tell me. Yes or no? Is this point clear? Very simple. So, very simply, you can see, for example, consider this grammar. Okay, A, S, B, or epsilon. Now you can easily see this is not regular grammar. Yes or no? This grammar is not regular grammar. This is not a regular grammar. Okay, because this is neither left linear nor right linear. Yes or no? You can easily see this is not a right linear grammar. This is not a left linear grammar. So this is not a regular grammar. But what is the language here? Here the language is also not regular. The language, that is standard grammar. This is a standard grammar for every A there is B. It is like A power n, B power n, where n is greater than equal to 0. Here you can notice the language is also non-regular. Okay, the language, that is also non-regular. Okay, understood. So I hope this point is clear, that a non-regular grammar can generate regular language or it can generate non-regular language. Is this point clear? So this is the note. So far what we have seen, this is the note, that if you have a regular grammar, if your grammar is regular, if you have regular grammar, then definitely language will be regular. Okay, you don't even have to check, the language will be definitely regular. Okay, but remember, if you have non-regular grammar, if you have non-regular grammar, then the language may or may not be regular. Okay, is this clear? If you have non-regular grammar, then you cannot say that language will be non-regular. Okay, is this clear? Simple point. You cannot say language will be non-regular, you cannot say that language will be regular. Okay, is this clear? So it may or may not be regular. If you have a non-regular grammar, then the language may or may not be regular. Either it may be regular, the language may be regular, or the language may be non-regular. So you can see these are the notes. Okay, please focus here. A regular grammar always generates regular language. This statement is true. A non-regular grammar may or may not generate regular language. A non-regular grammar may generate regular language, or it may generate non-regular language. Okay, so very simple. I hope you understood. Another example, you can consider this one. Here in this is the grammar, and focus here, is this right linear? Tell me, this grammar you look at and tell me, is this right linear? So you can see this grammar, because of this rule, this is not right linear. Yes or no? This is not a right linear grammar. This is not a left linear grammar. So this is not a right, this is not a regular grammar. Okay, this is not a regular grammar. And you can see this grammar will generate non-regular language. Okay, so what is the language generated here? Let's find out. If someone asks you what is the language generated here, then what that will be? That is very simple. What you can do, you can apply the substitution rule. You can apply the substitution rule. Okay, so if you apply the substitution rule, what you will get? You will get s. I can replace s with 0a. Okay, or there is 1b or epsilon. You can easily see that a will go to s0. Yes or no? Notice here, a will go to s0. A will go to s0 means what I can say, you can easily see when s will go to 0a, then this a I will replace with s0. Is this point clear? So remember, s is equal to 0. This a I will always replace with s0, because you can see a will always go to s0. So this a I will replace with s0. Or you can see this b I will replace with s1. So if s is going to 1b, then this b will go to s1. Okay, so you can see if s is going to 1b, this b will always go to s1. Okay, and there is already s going to epsilon. You can see this is the grammar, and this is a standard grammar for what? This is a standard grammar for, this is your even palindromes. Yes or no? This will generate even length palindromes, because here you can notice, for every 0, if you are starting with 0, notice what this s will generate. This s will generate the strings like this, that if you are starting with 0, then you will end with 0. Okay, in between there is s. Okay, 0 s0. So if you are starting with 0, you will end with 0, and in between there is s. If I replace this s with 1s1, if I replace this s with 1s1, then what I'm getting, again what I'm getting, you can see that, okay, 1 1. So you can easily see I'm getting palindrome here. If I replace this s, okay, remember this s, if I replace with 1s1, then again the same thing you can notice. Okay, so like this, I hope you are getting the point. So ultimately we are getting palindrome string. Okay, is this clear? So this will give us even palindrome, which is a non-regular, even palindrome which is a non-regular language. Okay, understood. So I hope all these points are clear. Okay, now let's move on now. So we have seen that if you have a regular grammar, it will generate regular language. regular grammar will generate regular language, but if you have known regular grammar, then it may generate regular language or it may generate non-regular language. Okay, is this clear? If you have regular grammar, it will definitely generate regular language, but if you have non-regular grammar, then it may generate regular language or it may generate non-regular language. Okay, so you can easily see here, you can notice we are mixing right linear productions and left linear productions. Yes or no? Like this is your right linear production, this is your left linear production. So you can easily see if you mix, please notice here, this is a note that if you mix left linear production and right linear productions, for example, this is right linear production, this is left linear production. If you mix right linear comma left linear productions in the same grammar, in this same grammar you are mixing left linear and right linear productions, then the grammar you are getting, this is not a regular grammar. And you can see the language is also, for this particular grammar, the language is non-regular, because this is the language, even palindromes, and this is not regular language. Okay, so just remember that you cannot mix in the regular grammar. Remember, you cannot mix right linear production and left linear production. You cannot mix. What is a regular grammar? Either it is fully right linear grammar. Regular grammar is either fully right linear grammar, or regular grammar is fully left linear grammar. Okay, so this is the idea. So you can see what is a regular grammar. Regular grammar is any right linear grammar or any left linear grammar. Here you can notice this is a right linear grammar, okay, and this is a left linear grammar. So remember, this is also regular grammar, this is also regular grammar. Is this clear? Now what are the languages generated here? Definitely language will be regular, you already know, because this is regular grammar, this is a right linear grammar, so this is regular grammar, so this will definitely generate regular language. But what is that language? Similarly, this is also left linear grammar, so this will generate regular language. But what is that language? The question is asking which languages are generated by these grammars. So you can easily find for this grammar what are the language generated. You can notice as, either I can replace this as with AB or I can replace with A. Okay, so here you can easily see from this as what I can generate. I can generate string A, I can generate string ABA. Okay, what I can generate from this S, I can generate string like ABS. Then this S I can replace with ABS. Already AB is there. This S I can replace with ABS. You can easily see this S I can replace with ABS. Okay. So finally, this S I can replace with A. So you will get AB, AB, and then A. So you can easily see this type of strings we will get AB, AB, A, and so on. So finally, what are the language here? Tell me. The language generated by this grammar. Okay, let's call it grammar G. So the language generated by this grammar, that will be AB whole star A, or you can say A BA whole star. Okay, both are same, both are equal. Okay, so you can say it's like AB whole star A, or you can say it is like A BA whole star. Okay, because if you notice, we have already seen this Y X Y Z whole star, sorry, X Y X whole star, X Y X whole star. This is same as X Y star X. Yes or no? So this property we have already seen in the regular expression chapter, because here what you will get, here you will get X Y X Y X. So it is like this. You will get this X Y X Y X Y X, and what you will get here, you will get X Y X Y X Y X. So both are basically same. Okay, so this property we have already seen in the regular expression chapter. Okay. Now let's see what are the language generated by this grammar. This is a regular grammar, so the language will definitely be regular. Yes or no? This is a regular grammar, because this is left linear grammar, so this is a regular grammar. Definitely language will be regular. Okay. If the question is asking is the language regular, you don't even have to check. Yes, this will be regular language. Okay, but what is that language? If the question is asking you what is that language, so what to do here? Very simple. Remember, you can apply the replacement rule. This B will always go to small a. Okay, yes or no? This B will always go to small a. So you can apply the replacement rule. I can say substitution rule. So substitution rule you can apply, because you can notice whenever A will go to B, this B will always go to A. Yes or no? This B I will always replace with A. So it is like this, AAB, and then A can generate AAB. This B, remember whenever A will go to B, this B will go to A. So ultimately I can say it is like this. Okay, and there is B generating A. Now you can notice in this, can you focus that this B is unreachable from the start state? Yes or no? From the start variable, can I reach B in this grammar? In this grammar, tell me, from the start variable, can I ever go to B? From the start variable I can go to variable A, but from the variable A I cannot go to variable B. Yes or no? So this variable has become unreachable, so you can remove it, because this has become unreachable. This became unreachable, so I removed it. Okay, finally this is what I got. Okay, now you tell me what this will generate. From here, what you can generate? Here you can generate AB whole star A. Yes or no? Very simple. AB whole star A. Because here, okay, there is this AB. So it will be like this. From this A, you can generate like this. That from this A, you will generate AB. Then this A you can replace with AAB. Okay. So like this. So ultimately, this A you can replace with A. Finally, this A I can replace with A. Okay. So remember, your answer will be AB whole star A. Or the same thing you can also write as the same expression. You can also write as AB whole star. Sorry. The language will be what? The language will be AB whole star. Okay. This will be the language. AB whole star. Is this clear? You can notice A, then AB whole star. This will be the language here, because you can see A, then AB whole star. So very simple. Okay. Now you tell me what this S will generate. From the start variable, what you can generate? From this variable, what I can generate? So you can see this will go to A followed by AB. Okay, you already know what A is giving you. A is giving you AB whole star. This is what A is giving you, followed by AB. Okay, so your answer will be this. So you can see the language. If you notice, the language is A, then any number of AB, then AB. Okay, can I mix these two? Can I mix these two? I can say it will be like AB whole plus AAB whole plus. Okay, very simple. Now let's move on. Now let's see equivalence of regular grammar and finite automata. Did you understand everything so far in this lecture? Whatever we have seen so far, did you understand? Let me know. So now let's study equivalence of regular grammars and finite automata. We have already seen that regular grammar will generate regular language, and we know that for regular languages we have finite automata. So basically, let me tell you that regular language, if you have any regular language L, if you have any regular language L, then for this regular language, tell me what are the structures that we can create to describe this regular language. What are the models? What are the structures we can create? We can create three type of structures. We can create three type of structures to define regular languages. Okay, to define regular languages. What are those? We can create finite automata. Yes, correct. We can create finite automata. We can create either DFA or we can create NFA for regular language. For every regular language, you can create DFA. For every regular language, you can create NFA. The language of DFA is regular language. The language of NFA is regular language. Okay, or what I can do? For any regular language, I can create regular expression. Yes or no? I can create regular expression. Okay, and what another thing that I can create for any regular language? I can create regular grammar. Okay, I can create regular grammar. Either I can create left linear grammar. Okay, you can also create right linear grammar. So you can see for every regular language there is left linear grammar. For every regular language there is right linear grammar. For every regular language there is DFA. For every regular language there is NFA. For every regular language there is regular expression. Okay, is this clear? So all these things, these are basically equivalent. DFA, NFA, regular expression, LLG, RLG, left linear grammar, right linear grammar. Okay, all these things are basically equivalent. So you can see for any regular language, three models are there to describe regular language. If you want to describe regular language, then there are total three models. We have finite automata, DFA, NFA, we have regular expression, we have regular grammar, LLG, RLG. Finally, I can say that these things are all equivalent. Like I can say DFA is equivalent to NFA is equivalent to regular expression is equivalent to left linear grammar is equivalent to right linear grammar is equivalent to regular grammar. Okay, is this clear? All are equivalent. What that means? Equivalent mode, that means all of them they describe regular languages. Yes or no? All of them they define, or I can say describe, or I can say they represent regular language. Regular languages. So all are basically equivalent. For every DFA there is NFA, for every NFA there is DFA, for every NFA there is regular expression, for every regular expression there is NFA. Okay, so you can see if you have a left linear grammar, then for the same language you can create NFA, for the same language you can create regular expression. Basically all these things are basically equivalent. Okay, their expressive power is same. Yes, their expressive power is same, their computational power is same. I can say their language recognition power is the same. All of them will recognize regular languages. If, for example, there is a language L, for this language L, if you have NFA, then for this language you have regular expression also, you have left linear grammar also, you have right linear grammar also, you have DFA also. Okay, so very simple point. So they have same expressive power. I can also say that they have same computational power because they recognize same set of languages, same class of languages. Their language recognition power is basically same. Okay, now so you can easily see all these are definitions of regular languages. Okay, read this. Regular language, many views, there are many views for regular languages. Okay, what is a regular language? L is regular language if you can generate it from right linear grammar, or regular language is generated from left linear grammar. It is accepted by some DFA, it is accepted by some NFA, it is generated by some regular expression. So you can see all these they will describe, they will define regular languages. Now let's see converting right linear grammar to NFA, also converting NFA to right linear grammar. So this is what we need to study now, that we will convert a right linear grammar to NFA. Also, we will convert NFA to right linear grammar such that language will be same. Of course, the language should not change. Okay, we are converting this RLG to NFA such that the language should not change. The language must be same. Okay, so when it will be useful? It will be useful in, for example, in the GATE exam. Let's assume this right linear grammar is given to you. Okay, and you want to find what is the language. Then what you can do? You can convert this to NFA, and then from the NFA you can find the language. So this is what you can do. Okay, now let's see how to convert right linear grammar to NFA. Also, how to convert NFA to right linear grammar. Okay, so first let me tell you few things. If you see any right linear grammar RLG, then in this RLG what components I have? There are total 4 components. Okay, we have set of variables, there are alphabet symbols. Okay, and we have start variable, and there are production rules. Okay, and if you know, if you see in NFA what we have, total 5 components we have start state. Okay, and there is set of states. You can easily see there is set of states, there is alphabet, there is initial state, there are transition rules, yes or no, and there are set of final states. Okay, so now you notice what are the similarities. Okay, see, in the right linear grammar we have sigma, which is the set of alphabet symbols, or I can say set of terminals. Okay, so for this in the NFA also we have set of alphabet symbols. Okay, in RLG, in the grammar what we have start symbol. Okay, so in the NFA what we have the start state. In the right linear grammar we have a set of variables. Okay, so here you have set of states, and in the right linear grammar you have production rules, here you have transition rules. Okay, is this clear? So these are the similarities I can say between right linear grammar and NFA. Is this clear? So you can easily see the start variable of grammar will basically behave like start state of the NFA. Okay. The variables of the grammar will behave like states of the NFA. The production rules will behave like transition rules of the NFA. And the alphabet symbols, the terminals, they will behave like alphabet symbols. Okay. So this is the idea. Now let's see how to convert this RLG if you have a right linear grammar and if you have NFA, then how to convert them to each other. Okay, we want to convert NFA to grammar and grammar to NFA. Okay, so let's see. In the right linear grammar, which type of productions are allowed? Tell me. Tell me which type of productions are allowed in the right linear grammar. So you can easily see we have this type of production. For example, a variable can go to, okay, for example, let's assume this variable A you have, and this can go to, for example, B, B, yes or no. This type of production rule we can have in the right linear grammar. We can have this type of rule. So if you have this type of rule in the right linear grammar, then in the NFA, what you will do? I told you states will become these variables will become the states. Yes or no? We have already seen variables will become the states. Start variable will become the start state. The production rules will become the transition rules. Okay, so you can see the variables will become the states. Okay, so in the NFA, remember what will happen? These variables will become the states. Okay, and this production rule will become the transition rule. So it will be like this: from A on B we are going to B. Is this clear? From A on B we are going to B. This is very intuitive. Yes or no? Basically from the variable A on B we are going to B. Okay, so remember, when you have this production rule in the grammar, in the right linear grammar, if you have this rule, then when you convert this to NFA, okay, then what will happen? These variables will become the states. Okay, and this rule will become the transition rule. So you can see it will be like A on B, it is going to capital B. Okay, understood? And similarly, remember, you can convert NFA to regular this to right linear grammar. Okay, so if you have this situation in the NFA, if you have this transition in the NFA, then remember this transition will become this rule in the right linear grammar. Okay, is this clear? So very simple point. For example, in the NFA, if you have this transition rule, then in the grammar, what you will write? In the grammar, you will write that, okay, A is going to BB like this. Okay, I hope you understood. This is very simple, intuitive. Now let's see another. For example, in the grammar, we can have this type of rule. Okay, A can go to maybe A, B, capital B. Yes or no? So what we will do, let me know. Very simple. This A, these variables will become the states. Remember, variables will become the states. From this A, on AB, we will go to B. Okay, is this clear? Very simple. So remember, from A, on this AB, we are going to B. Understood? So these are very simple things. Now let's see the next one. For example, if you have A going to BA, now tell me what to do. Very simple. So this variable will become the state. So this variable will become the state. And remember, A is going to BA. That simply means A on B, it is going to A. A on B, it is going to A. Okay, so this self loop will be created. Is this understood? Please tell me how to convert production rules of right linear grammar to NFA. So far, is everything clear? Let me know. Now let's see the next one. What more production rules are can be there in the right linear grammar? Which type of production rules can be there? Let me know. For example, you can have this rule that A can go to B. This variable A can go to variable B. So how to convert this to NFA? In the NFA, what will happen? I told you these will become the states. Yes or no? I told you variables will become the states. Okay. So how to make the transition? Very simple. Remember, this you can think as A is going to epsilon B. Can I think? Tell me. Can I think like this? Very simple. Remember, A is going to B. So can I think like this, that A going to epsilon B? Or you can think that this is the null move. Yes or no? From A, you are directly jumping to B. From A, I am jumping to B. Okay. So you can basically say that it will be like this. There is a null move. Okay, understood? Because from A, I am jumping to B. So you can see I can write like this. There is a null move. Or you can think like this. A going to epsilon B. This is how you can think. Okay. Now let's see the next one. What else is possible? I told you that the start variable will become the start state. Okay, is this clear? The start variable, what it will become? It will become the start state. Okay, so this start variable, this is going to become the start state. Here you have start variable, and here it will become start state. Okay, what else you can have in the right linear grammar? Tell me. In the right linear grammar, which type of productions you can have? For example, you can have this production. A variable can go to a sequence of terminals, for example, a going to a. Yes or no? I can have this. Agree? So what to do now? This, what to do now? I told you these variables will become the states. So this variable will become the state. Okay, but on a, where are we going? But on a, remember, on a, where are we going? Tell me, where should I go on a? You can easily see this is a terminal. Yes or no? So here the grammar will stop. Do you agree with me? Okay, here the grammar will stop. Basically, string is generated. So this will become the final state here. Here this will become the final state. Okay, because notice one thing. In the grammar, see, very simple point. In the grammar, actually, here the string will be generated. Do you agree? For example, if you have this type of situation like a, b, okay, a is going to a, okay, or b is going to b. Now you can notice in the grammar what happens. Here we have non-terminal. This will go to variables, but you can notice when this will go to terminal and when this will go to terminal, then we are getting the string. Yes or no? Then the string is generated. Do you agree with me? Then the string is generated. Okay, so remember these rules. If you look at these rules will help you generate the string. These rules are helping in the generating string. Yes or no? Finally, okay, finally, these rules will help you generate string. Do you agree? Finally, these rules will help you in generating the string. I hope this point is clear. Okay, finally, these rules are helping generating string. So that is the reason I am saying that if you have this type of rule, a going to a, then what you can do, basically, this a you can just go to some final state. Okay, very simple. Now tell me about this one. If I have this type of rule, a going to a b, maybe a b. Now tell me, what about this one? Let me know. Very simple. This will help you generate the string. Yes or no? Finally, at the end, this will help you generate the string. Okay, so remember on AB, you will go to final state. Okay, agree? Let me know. And what about this one? Interesting. What about this one? A goes to epsilon. What about this production? How to create here? Let me know. For this production, how to create the transition in NFA? So it is very simple. Here, basically, A is going to epsilon. So this A itself, you can make final state. This a itself you can make final state. Yes or no? That's it. Okay, so this transition, in this transition you can just make a as the final state, because remember, anyway, if you apply the same thing, for example, from a, basically on null move you are going to final state. Okay, these two are same or not? See, from the state a, without reading any symbol, you can go to final state. From state a, without reading any symbol, I can go to final state. So I can simply say that a is the final state. Okay, is this clear? So very easily. So what you can do for this rule, you can just make final state. I hope this point is clear. Okay. So remember this point, that if you have this rule, A is going to epsilon. When you have this rule, then what you will do? This A itself you will make final state. And remember, when you have this rule, for example, AB, then what you will do? From A, on AB you will go to final state. Okay. So we have seen every type of rule that is possible in right linear grammar. And tell me, what about this one? A going to AB. What about this one? How to convert this rule to NFA? Let me know. This rule, how to convert to NFA? First of all, I am converting regular right linear grammar to NFA. I am converting right linear grammar to NFA. So this is not even allowed in the right linear grammar. Yes or no? This rule, this is not even not allowed in right linear grammar. Understood? Please tell me. So this is nonsense. Okay, is this clear? This is not allowed in the right linear grammar. So that's it. This is the complete summary. Basically, how to convert right linear grammar to NFA and how to convert NFA to right linear grammar. Please tell me, did you understand? Let me know. Let me know. So we have seen everything now. So you can easily see these diagrams. In the right linear grammar and NFA, what are the comparisons? In the right linear grammar, we have start variable. So in the NFA, we have start state. In the right linear grammar, we have set of production rules. So here you have set of transition rules. In the right linear grammar, your variables, they will become states in the NFA. And this is alphabet symbols, so they are alphabet symbols. Okay, you can easily see. Look at this. If you have this production in the right linear grammar, A is going to AB. So in the NFA, what you will do in the NFA, these variables will become the states. Okay, so you will do A on A, it is going to B. For example, what about this? You can see A on AB, it is going to B. Okay, remember one more thing. One more thing. This AB, you might be thinking, is there anyone here who might be thinking, sir, this type of production we cannot put in the NFA? In the NFA, can we do this AB? See, in the NFA, can we make this type of age? In the NFA, can we make this type of age? We cannot make this type of age. Actually, this is equivalent to it's like this. Okay, it is like this. That first A should come, then you go to some dummy state, and then B should come. Okay, is this clear? So they are basically equivalent. Is this point clear? Let me know. Is this point clear? So remember, when you say that A, we are going to be on AB, okay, then it is basically first A should come, then B should come. Here, this is some dummy state. You can just create some dummy state you can create. Okay, is this clear? So, like this. Anyway, you can just keep like this, no problem. Okay, the language will not change, so you can keep like this. This is what I'm saying, that if you have this production rule in the right linear grammar, okay, then what you can do, A on AB, it is going to B. Okay, so like this. Now, let's see the next. A going to B, it is like null move, because I told you, you can think like this. A going to epsilon B, so it will be like this. A null move to B. Okay, and what about this one? I told you final state you will make. So from A on A, you are going to final state. And what about this one? The self loop will be created on A. Next, this rule is not allowed in the right linear grammar. Yes or no? This rule, this is not allowed in the right linear grammar. Okay. Next, you can see, what about this rule? So here the A state, this state will become the final state. Yes or no? This A itself will become the final state. Okay, so very simple point. I hope all these points are clear. Now let's move on. Now let me tell you one thing, that converting right linear grammar to NFA, this is sometimes useful. Okay, we will see in the gate PYQs, in the gate exam, we will see that sometimes it is useful. If a right linear grammar is given to you, this grammar is given to you, then the question will ask you that what is LG? Okay, then what it is useful. Remember, sometimes maybe it is complicated, maybe you are not able to find the language. Then what you can do, you can convert to NFA, and then from the NFA you can find the language. Okay, is this clear? So remember, converting this grammar, right linear grammar, okay, to NFA, this is sometimes useful. But converting NFA to right linear grammar, this is actually never useful in the gate exam. In the gate exam, this is never useful. So remember, in the gate exam, if a finite automata is given to you, NFA or DFA, any finite automata is given to you, then don't convert that to right linear grammar. Okay, because this will never be efficient. Okay, is this clear? So very simple point. But remember, this is sometimes useful, that if a right linear grammar is given to you, you can convert that to NFA to find the language, to find LG. Let's see this example. Here, this grammar is a right linear grammar, because you can notice in every production rule, we have at most one variable on the RHS, and that variable is on the rightmost position. So this is a right linear grammar. Can you convert this grammar to NFA? Let me know. So very simple point. What we need to do, we need to convert this grammar to NFA. Find NFA. Okay, so this is what we need to, we need to convert this grammar to NFA. Okay, so let's do that. Tell me what will happen here. I told you this will become the start state. Yes or no? In the NFA, this will become the start state. This is the start variable. This is the start variable. Because this is the start variable, so this variable will become your start state. So I can say this variable itself, this will become your start state. Okay, this is the first thing. Next, you can notice, look at this transition. For this transition, what will happen? This transition means that from V0 on A, I will go to V1. Yes or no? So the same thing I will do. From V0 on A, I will go to V1. Okay, understood? Next, what about this transition? Here what I will do, from v1 on ab I will go to v0. Yes or no? From v1 on ab I will go to v0. So remember, from v1 on ab, on a followed by b, on ab I will go to v0. Okay. And what about this one, v1 going to b, v1 going to b? So what about this one? I told you, you will create a final state here. So v1 on b, we will go to a final state. Okay, so remember, it will be like this, v1 on b, we will go to a final state. Understood? Please tell me, let me know. So this is how you can create NFA. So finally remember, this is the NFA you will get. Okay, and now you can easily find what will be the language. So can anyone tell me what will be the language here? What is the language? From the NFA you can very easily find the language. Actually, the language will be what you can easily see. This is the start state, so this loop will be there, and then at the end you must have AB. It is like this. Are you getting my point? This loop will be there. It will be like a, then AB, A, then AB. This loop will be there. A, then AB. Yes or no? Is this clear? First A, then this is AB, remember. So it is like A, then AB, A, AB, A, AB, A, AB, A, AB. And then finally you are here. Okay, from here, A, AB will take you to final state. So your answer will be this. Your answer will be A, AB whole star AB. Okay, understood? Is this clear? See, notice one thing. You are in the initial state. In the initial state, if you make this loop, ultimately where you will go? You will go to state V0. Yes or no? Notice. You are here. You are standing here. Okay, now if you make this AAB, then now you are in the V0. Next AAB, now you are in the V0. Next, you are in the V0. So remember, this AAB whole star will keep you in the V0. Now you are in the V0. Now from V0, you need AB to go to final state. Okay, so remember, after this AB whole star, you need AB to go to final state. So this will be your language. Okay, so like this you can easily do. I hope you understood. Now let's move on. So we have seen everything. I told you that how to convert this production rule in the right linear grammar. If you have this production rule, then in the NFA what will happen? You can see this V0, this will become the initial state. I told you this start variable will become the initial state. Okay, and you can see from V0 on A we are going to V1. So finally you can see, you can easily convert. Okay, this will be your final answer. We have already seen. Now let's move on. Let's see this right linear grammar. Let's convert this right linear grammar to NFA. Again, the same question. Here, first of all, you check, is this right linear grammar or not? Let me know. Is this grammar right linear? Yes. You can notice every production is right linear production. So yes, this is a right linear grammar. Okay, yes or no? So this is regular grammar also. Now what you need to do? You need to convert this right linear grammar. Okay, you need to convert this right linear grammar to NFA. Okay, this is what you need to do. So tell me what you will do. You know that this will become the initial state. Yes or no? In the NFA. In the NFA, this S, this will become the initial state. Okay, agree? Start variable will become the start state, because here this is the start variable. Okay, variables will become the state. Very simple point. Variables are going to become the state. So start variable will become the start state. Okay. Then you can notice, what about this production rule? Here you have from S on AB, we are going to S. Okay, is this clear? From S on AB, we are going to S. So that is basically self loop. Okay, what about this one? S going to A. Tell me, S going to A. So epsilon, yes or no? Is this clear? I told you that whenever you have this type of situation, V1 going to V2, then what you can do? Then this will become like this, V1, V2, null move. Agree? Because remember, this V1 going to V2, you can think like this, that V1 is going to epsilon V2. You can think like this. So very simple. Okay, what about the next? A going to BAB. Okay, remember A on BA, B followed by A, we are going to B. Remember, the variables will become the state, you already know. Okay, all the variables are going to become the state. The variables will become the states. Okay, variables in right linear grammar, they will become states in NFA. Okay, so this is the simple point that we already know. Now, what about this one? B on A, it is going to A. Yes or no? B on A, it is going to A. And what about this one? here this will help you create the string, yes or no. This will finally at the end, finally it will generate the string, it will help you generate the string. So remember, from bb we are basically going to final state. Okay, understood? Please tell me. So very simple point, from here on bb we are going to final state. So this is the nfa that you will get. Please tell me, did you understand? Let me know. Now what is the language here? Let's see the language. So we have already created the nfa. The nfa is like this: you have a start state, okay, and there is a self loop. The self loop is on ab, a followed by b. Okay, then there is a null move, and we are going to state a. Okay, in the state a we have a loop. Okay, we are going to state b on ba, and then we are coming back on a. Then you can notice, from this b we are going to final state on bb. Okay, so this is the idea. Now you tell me, what is the language here? If this is your nfa, then what will be the language? That is very simple. See, this loop you can take any number of times. Yes or no? ab whole star. I want to go to final state, so ab whole star, then null move. Okay, yes or no? First ab whole star, then null move. Then now where I am, now I am standing here. Remember, now I am standing here. In this state, what I can do? I can do baa. This loop I can take any number of times. Yes or no? ba a. This loop I can take any number of times. You can notice BAA, 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 BAA. So finally, after taking this loop any number of times, I will be here. I will be here. Okay, so then what I need to do? Then I need to take BA, then BB. Then I need to take BA, then BB. Okay, this will be the language. Understood? Very simple point. Okay. So we have already seen this one. How to convert this? This is the right linear grammar. How to convert this to NFA? We have already seen. Okay. Tell me about this one. This right linear grammar is given to you. First, you tell me, if the question is asking you what the language, can you directly find this grammar? You can easily see this is the right linear grammar. First of all, okay, this grammar is given to you. You can easily see actually this is right linear grammar. Okay. Now you tell me what the language here. You don't have to convert to NFA. Remember, you don't have to convert to NFA, because you can easily see here what is happening. See, S is either going to 0 or it is going to 1t. Look at t. T is going to 0t or 1t or epsilon. Okay, do you remember, this is a standard context free grammar. This is a standard grammar for a or b whole star. Yes or no? This is like 0 or 1 whole star. This we have already seen in the previous lecture. This is a standard grammar for 0 or 1 whole star. For sigma star, you can generate any string here, whatever string you want, any string you can generate here. So tell me what S will generate then? From S, what you can get? Either you can get string 0 or you can get 1 followed by sigma star. Okay, is this clear? So your answer will be this. You can easily find. Okay, understood? Now, what is another method to find the language? See, this is method number 1. There is another method to find the language. What that will be? Let's find the language L of. Okay, so what you can do? This G you can convert to NFA. You can convert to NFA and then you can find the language. So what will happen? This will become the start state. Okay, so on the start state on 0, where are you going? Tell me. What about this rule? This rule, we will go to final state. Yes or no? We will go to a final state. Okay, next. What about this rule? As on 1, we are going to state T. Okay, T going to epsilon. So T will become the final state. Yes or no? This, because of this rule, what will happen? This T will become the final state. Okay, agree? We have already seen this. T will become final state. Then you can see that T 0T. So there is a loop on 0. There is loop on 1 also, comma 1. Okay, so you can see there is loop on 0, there is loop on 1. Now can you find the language here? Tell me what is the language? This is final state, this is final state. So the language will be this string 0 is accepted. Okay, what else is accepted? You can see 1 followed by anything. Yes or no? 1 followed by anything. So this will be your language. So remember, if a right linear grammar is given to you, then how to find the language? If a right linear grammar G is given to you, Okay, then to find LG, what you can do, it must be a right linear grammar. Okay, it must be a right linear grammar. So if a right linear grammar is given to you, then to find LG there are two methods. Okay, the method one, from RLG you directly find the language. Okay, you directly find the language, correct? From the regular grammar, from the grammar you directly find the language. Or what you can do, you can convert this right linear grammar to NFA, and from this NFA you can find the language. Okay, is this clear? So there are two methods. Whichever you like you can apply depending on the grammar. If the grammar is very complicated, if you cannot directly find the language, then you can convert to NFA and then you can find the language. Okay, so there are two ways and you can use any of them. Understood? Please tell me. So we have seen. Now let's see how to convert DFA or NFA to right linear grammar. To right linear grammar. Okay, so let's see this. Means if a DFA or NFA is given to you and we need to convert this to right linear grammar. Tell me one thing. Will you convert DFA or NFA to right linear grammar to find the language? Means if a DFA NFA is already given to you, okay, and then tell me to find the language, will you convert this to right linear grammar? Don't do that. Okay, to find language, if the question is asking you language, then don't do this conversion. Okay, so when this conversion you need to do, tell me, then why should we study this conversion? Let me know. From NFA, from DFA or NFA, this can be either DFA or this can be NFA. Basically, this can be any finite automata. So how to convert this finite automata to right linear grammar? To right linear grammar. So why we should study this conversion? Because maybe in the gate exam, what they can do, they can ask you the right linear grammar. They will not ask you the language. They can ask you what? They can ask you right linear grammar. Are you getting my point? From the automata, they can ask you which option is the correct grammar for this automata. Are you getting my point? Please tell me. Okay, so this is the idea that in the gate exam they can give you some DFA or NFA and they can ask you in the options, they can ask you what the correct right linear grammar for this automata. Okay, then you can do this conversion because but remember, to find the language you don't have to do this conversion. Okay, so let's see how to convert DFA or NFA to right linear grammar. It is actually very simple. So let's see this. It is actually very simple. This NFA to right linear grammar, this conversion I want to do. Okay, I want to do this conversion. So this is actually very simple. In the NFA, if you have this type of situation that you have some state A and that is from that state A on A, let's assume you are going to B, then in right linear grammar what I will put? Tell me what I will put. Let me know. If this is the situation in NFA, then in the right linear grammar what will happen? Very simple. These states will become the variables. Yes or no? These states will become the variables. A will go to AB. The states will become variables. Very simple. I hope this point is clear. So, like this. Okay, very simple. What about this? From A, let's assume on epsilon you are going to B. Then tell me what you will create in the right linear grammar. It will be just A going to epsilon B, but that is same as A going to B. Yes or no? So it will be just A going to B. Okay, understood? Very simple. And what about the start state? If you have start state Q0, if this is your start state, then what this will become? This start state will become the start variable. Yes or no? This start state, this will become your start variable. It will become your start variable. Simple. Okay. What else? What else can you have? For example, if you have this final state, now tell me if you have this final state, A going to B, A on A, we are going to final state. So, what I will do here? Let me know. I will just put A going to A. Okay. Actually, I will put A going to AB. Okay. Sorry. I will put A going to AB. I will put like this. But remember, because this is the final state, because this is the final state, so what I will do, I will put this transition that B going to epsilon. Okay. Is this clear? See, very simple point. A on A, it is going to be A on A. It is going to be, so I can put that A is going to AB. But because this B is the final state, so I will put B going to epsilon. Is this clear? Please tell me. And what about the self loop? For example, if you have this type of self loop, on A, then what I will do? Very simple, A going to AA. Okay, understood? So like this, you can convert NFA to right linear grammar. I hope all these points are clear. Very simple. All these points are quite simple. Now let's move on. Let's see how to convert this NFA to right linear grammar. This is the question. Okay, convert this to this M you convert to right linear grammar. Okay, so do this conversion. Tell me what you will get. Very simple. I told you this start state will become the start variable. Yes or no? This start state, this will become your start variable. So let's make it start variable. This Q0, this will be your start variable, remember. Okay. And from this start variable, you can see on A, I am going to Q1. On A, I am going to Q1. Okay, understood? So this transition is done. What about the next Q1? Q1 on B, I am going to Q1, or you can see on A, I am going to Q2. On A, I am going to Q2. You can see very easily. So this Q1 is also over. What about Q2? What about Q2? Tell me. What about Q2? Q2 on B, it is going to Q3. Q2 on B, it is going to Q3. Q2 is going to BQ3. Okay. And what about Q3? Remember, Q3 is final state. So Q3 will go to epsilon because Q3 is the final state. Okay. What else? You can see Q3 is going to Q1 also. Q3 is going to Q1 also. So that's it. This is the grammar that you will get. Is this point clear? Let me know. You will get this right linear grammar. You can see. So in the GATE exam, if NFA is given to you, NFA or DFA, here you can see if this is given to you and the question is asking you what is the right linear grammar, then you can do this conversion. But to find the language, you don't have to do this conversion. Yes or no? If you want to find the language, then you do not have to do this conversion. You do not have to do. Okay, is this point clear? Please tell me. Very simple point, right? Okay, can you tell me what are the language? Like if this NFA is given to you and let's assume they ask you what are the language. Let's see what is the language here. Then tell me what that will be. You can easily see from the start state, I want to go to final state, remember? So first I will take this A. So the language will be like this. First I will take this A. Okay, now where I am? Now I'm standing in the state Q1. Here I am standing. Okay, now notice in the state Q1, there are two loops on in the state Q1. In the state Q1, there are actually two loops. What are those? In the state Q1, there are two loops. One loop is on B, one loop is on B, another loop is on AB. Yes or no? Notice. See, in the state Q1, there are two loops. Okay, there is one loop on B, and another loop is AB epsilon. It's like AB. So these loops can happen any number of times. Yes or no? This loop, also this loop, they can happen any number of times. For example, this can happen 3 times, then this can happen 1 time, then 2 times, then this can happen 4 times. Finally, you will stay here in the state Q1. Okay. So remember, at this time, I'm in the state Q1. Okay. So finally, from the state Q1, what I need to go to final state, I need AB. So this will be the answer. Is this clear? Please tell me. So this will be the language. Now you tell me one thing. In the GATE exam, if they ask you what are the language for this automata, will you convert this to grammar? This automata is given to you and they are asking what is the language. Think about it and tell me, will you convert this to grammar? No. If you convert this to grammar, then from the grammar, if you find the language, it will be very tedious, very time taking, very inefficient. That is the reason I'm saying that if the purpose is finding the language, if this is the purpose, that what will be the language, then never create finite automata to regular right linear grammar. Okay, is this clear? If your purpose is to find the language, then don't do this conversion. Okay, but this conversion is sometimes helpful. Means if the grammar is given to you, right linear grammar is given to you, then you can convert to NFA and then you can find the language. So this conversion is sometimes helpful. Okay, so we have seen all the points. So you can easily see that if you have this type of transition in the NFA, then in the grammar you will get Q0 going to AQ1, and this will become the start variable. And because this is the final state, so you have to put Q3 going to epsilon. Okay, because you can see Q3 is the final state. So in the grammar, in the right linear grammar, you will put Q3 going to epsilon. Okay, so very simple. Let's see this. Tell me, if the question is asking you language, then what that will be? For this machine, for this automata, if the question is asking what are the language, will you convert this machine to grammar? Will you convert this machine to right linear grammar? No, you can directly find what that will be. That will be a star followed by a, see, a star then followed by a, then b star, then b star, then followed by b, then c star, then followed by c. So your answer that will be basically a plus b plus c plus. This will be the language. Okay, but in the gate exam, what they can do for this, for this machine, for this NFA, they can ask you what is the right linear grammar. Yes or no? They can ask you in the options what is the right linear grammar. So tell me, what will be the right linear grammar for this NFA? That is very simple. Your start state that will become the start variable. So your start variable will become the s0. Okay, s0 on a it is going to s0. Also on a we are going to s1. Yes or no? From s1 on b we are going to s1. On b we are also going to s2. From s2 on c we are going to s2. Also on c we are going to s3. S3 is final state, so I have to put s3 going to epsilon, because this is the final state. Since this is the final state, remember this is our final state. Because this is the final state, so we have to put s3 going to epsilon. This we have to put because this is the final state. So like this, you can convert this finite automata to grammar. I hope you understood. Right linear grammar you got. Okay, understood? Let me know. So very simple. Let's see this example also. For this example, first you tell me the language. Let me know. This NFA is given to you, and you tell me what is the language. Actually, this is DFA. Okay, so this is DFA also, this is NFA also, because every NFA, every DFA is NFA. Yes or no? This machine, if you notice, this is actually DFA, but this is also NFA. Okay, now let's see how to find the language. You find the language. Tell me, what will be the language here? You can easily see, if you want to find the language, okay, then remember this dead state you can remove. Yes or no? What is this state? This is dead state. This is dead state. So remember, this part will not contribute in the strings generated. Do you agree with me? This part will not contribute in the language. Do you agree? This part, look at this part, and this will not contribute in the language. So what you can do, this is dead state, okay, and I want to find the language. So what you can do, you can just remove this part. Okay, just remove this part. Now tell me the answer. Now there are two final states. Okay, so your answer will be what? Answer will be basically what is the language accepted by S12 union the language accepted by S2. Okay, so tell me what is the language accepted by S12? That is only string 0. Or what is the language accepted by S2? That is basically 0, then either 0 or 1, and then 0 star. So this will be your final answer. Understood? Now, let's do final practice. This DFA or this NFA, basically this finite automata that you have, can you convert this finite automata to right linear grammar? Can we convert this machine to right linear grammar? Yes, very easily. This start state will become the start variable. Okay. Now you can see this start variable. On 0 it is going to S12, or on 1 it is going to S. Correct? Okay. What else? You can see this S12. On 0 it is going to S2. On 1 it is going to S2. And remember, S12 is final state. So epsilon, do you agree with me? Because this is the final state. Remember, this is the final state. Here you can notice this state is final state. So what we will put? We will put S12 is going to epsilon. This also we will put. So that is the reason we are putting this one. Okay, clear? Next you can see, what about S2? S2 on 0 it is going to S2. On 1 it is going to S. S2 on 1 it is going to S. And remember, S2 is also final state, so we will put epsilon. Understood? And then finally this state S. This state S, on 0 it is going to S. On 1 it is going to S. Okay. So very simple, I hope you understood. So this will be the right linear grammar. Okay, understood? Let me know. One more thing I want to tell you, that is, in the gate exam, let's assume this NFA is given to you, this DFA NFA, basically this finite automata is given to you, and let's assume in the options they are asking you what is the correct right linear grammar. Correct right linear grammar. Then of course this grammar is correct. But maybe what they can do, remember, maybe what they can do, they can remove this final dead state, because this is anyway dead state. This is a dead state, so we can remove this dead state. Okay, in the gate exam, remember, if this automata is given to you, this automata, if this is given to you, and they are asking you find the right linear grammar, then remember this answer will be correct on your screen. This answer is correct. But another option is possible, that is, see, you can remove the dead state, because this dead state will not contribute in the strings in the language. Yes or no? So here, remember, after removing this, now you can notice this is also gone. Okay, now you can notice from S0 on 0 we are going to S12. Okay, so you can see this is also gone. So finally it will be just simply epsilon, and these productions also will be gone. Okay, so that's it. I hope you understood. So this is also correct. Remember, you can remove the dead state. You can remove the dead state. This grammar is also correct. This right linear grammar, this is also correct. And this right linear grammar, this is also correct. Okay, you can just remove the dead state. Okay, so very simple. So I hope you understood everything so far. Now let's see a note about left linear grammar. So far I have discussed right linear grammar. Did you notice that how to convert right linear grammar to NFA, and how to convert finite automata, DFA or NFA, finite automata, to right linear grammar? This is what we have seen so far. Do you agree? Okay, so our focus is fully on the right linear grammar, that how to convert right linear grammar to NFA, and how to convert NFA to right linear grammar. Yes or no? This is what we have seen so far. Okay, but what about left linear grammar? What about these grammars? So let me tell you a note about left linear grammars. Okay, and what is that? Read this note. In the left linear grammar, if you reverse every production rule, in the left linear grammar, if I reverse every production rule, then I will get right linear grammar, but the language will also reverse. Okay, see, understand this what I'm saying. If you have left linear grammar, let's assume you have left linear grammar G. Okay, and this grammar is accepting, generating some language L. Yes or no? The language, let's assume the language is basically L. Now in this grammar, in this grammar, if you reverse every production rule, if we reverse every rule, if we reverse every rule, okay, remember, if you reverse every rule, then what you will get? Then you will get left linear grammar. Let me call it G2. Okay, you will get sorry, in the left linear grammar, if you reverse every rule, you will get right linear grammar G2. But let me tell you, the language will also reverse. Okay, the language, what the language will be? If you see the language of this G2, that will be L reverse. Okay, so this is the simple point, that if you have a left linear grammar, and let's assume the language is L, then if you reverse every rule, if you reverse every production rule, then the new grammar will be right linear grammar, but the language will also reverse. Okay, is this point clear? Please tell me. Let's see some examples. With example, this point will become very clear. Let's consider this left linear grammar. Can you tell me what is the language here? This is the left linear grammar. You can easily see this is LLG, left linear grammar. Okay, so what is the language here? You can easily see this A, what it will generate? It will generate A star. Correct? Okay, you have S going to AB and A going to AA or epsilon. So let me tell you, if you look at this production, okay, this rule, if you look at this rule, this from here I can say that this A will generate A star. Okay, from A I can generate A star. So from S what I can generate? From S what I can generate? S goes to AB. So it will be like A star B. Yes or no? So the language, finally the language, remember, for this if you notice, finally the language is A star B. Okay, so very simple. Now let me tell you one thing. that if you convert this grammar, this is a left linear grammar. Okay, what you do, if you reverse every rule, okay, what you do, you reverse every rule, every rule. So if you reverse every rule, what you will get? If you reverse every rule, then remember you will get s going to be a. Okay, when I say reverse every rule, then remember you don't have to do ab going to s. Okay, is this clear? Don't do that. Don't do that. When I say reverse every rule means reverse the RHS of every rule. Is this point clear? Please tell me. So when I say reverse every rule, that means reverse the RHS of every rule. So you will get s going to ba, a going to aa slash epsilon. Now you can easily notice this is a right linear grammar. Yes or no? This is a right linear grammar. And tell me what the language here. For this left linear grammar, the language was a star b. Okay. Now you got, when you reverse every rule, then you got right linear grammar. And what are the language for this right linear grammar? The language, tell me, the language that you can easily see. If you see, that will be ba. Okay, from s ba, a will generate a star, so it will be like ba star. You can easily see. Okay, from s we will go to ba. Now this a will generate a star, so you will finally get ba star. And can you notice this is the reverse of l? Can you notice this language is the reverse of l? This this is l reverse. Okay, understood? So this is what I am saying. I hope you understood everything so far. So remember, very simple point. If you have a left linear grammar G, okay, so let's see this note, that if you have a left linear grammar G, and let's assume the language is L. Okay, for this, let's assume the language is L. Okay, in this grammar, if you reverse RHS of every rule, RHS of every rule, if you reverse RHS of every rule, then you will get a right linear grammar. Let's call it G2. But the language will also reverse. Okay, the language will become L reverse. Understood? Simple point. Okay, so that's it. So this is what we have seen. That's it. This is your chapter. We have seen all about regular grammars. We have seen right linear grammar. We have seen left linear grammar. We have seen regular grammars. Every point we have seen. We have seen how to convert right linear grammar to NFA and how to convert NFA to right linear grammar. Okay, we have seen some points about left linear grammar, and we have seen regular grammars also. I told you that if you have a regular grammar, it will definitely generate regular language. But if you have non-regular grammar, then it may generate regular language or it may generate non-regular language. Okay, so every point that we have seen in this lecture, every example that we have seen, please tell me, did you understand? Let me know. So this is the complete lecture. All the details related to regular grammar, right linear grammar, left linear grammar, we have already seen in this lecture. Okay, so thank you everyone. Thank you.